Hello students, in this video we'll consider the square root function as a conformal mapping. Let's consider the holomorphic function f of z is the square root of z. Now to tell you what this is equal to the exponential of 1/2 the log of z, where log of z is the log of the modulus of z, where this is our ordinary natural logarithm, because that's a real number, okay, what we know from calculus, plus I theta, and here theta is between negative pi and pi. So I'm making a branch cut along the negative real axis. So the branch cut is along the negative axis. Okay, excellent. Okay, and so in this case, what can we say? So we can actually simplify this now. So now I know the domain of the square root. The domain of the square root is the complex plane. Here's the x-axis, here's the y-axis, and of course our branch cuts right over here. Okay, so what can we do? Of course we can write, now writing z is equal to r e to the I theta, I'm going to write this, I'm going to assume that theta is in this range over here, right? So my theta has to be in this range, okay, to do it correctly. All right, this is going to be what? Then this implies that the log of z is going to be what? Is going to be the log of r, plus I what? Plus I theta. Good. And now I can fill that into this formula over here, right? So hence, we have the following. What do we have? We have that the square root of z is equal to the exponential of 1/2 log r plus I theta, okay? And so this is going to be the exponential of r over log of square root r, because the modulus is a positive number, right? Plus I theta over 2. Excellent. And so now, of course, we use properties of exponents, right? And so this is going to be equal to what? This is going to be equal to just the square root of r. And then I'm going to have e to the I theta over 2, so I'm going to have cosine of theta over 2 plus I sine of theta over 2. Okay? And so what does this tell me? This tells me what my u and my v are, right? So this implies that my u, this is u plus iv, where u is going to be what? U is just going to be square root of r cosine of theta over 2 plus I square root of r sine of theta over 2. Okay, that's the polar form of the square root, okay? And that's what we use for de Moivre's formula, right? How we compute roots of these numbers over here, okay? Excellent. So now let's address two simple questions. So here's the first question. So my first question is if I look at the whole domain of square root over here, except for that ray, what's going to happen to all these points over here? Let's figure it out. That's our first question. So question, f maps the entire complex plane minus the ray, negative infinity 0, into what region? Okay, let's think about it. All right, so what's going to happen over here? So I'm going to break this into a couple different cases. Let's first consider the case where we're in the right half plane, okay? So let's suppose the real part of z is greater than 0, okay? What does that mean your argument's between? Your argument's between negative pi over 2 and pi over 2. This implies that the argument of z is in the interval negative pi over 2 to pi over 2. Okay, that's your theta. So what's going to happen over here? And then the r can be anything, right? R is just greater than 0, right? So your r is greater than 0, right? Your r is greater than 0. And now what's happening over here to your I theta, all your arguments, when you plug them into the square root, the arguments get cut in half, right? So all the arguments are cut in half. Therefore, the argument of root z for this real part of z greater than 0 is going to be between negative pi over 4 and pi over 4, okay? So in other words, what's happening over here is the square root is taking the what? The square root is taking the right half plane, like that, and mapping it where? And mapping it to this sector over here. like that. There's my u and there's my v over there. Okay, excellent. And this, of course, this angle over here is what? This angle, this measured angle, is exactly what? It's exactly pi over 4. So what is the square root doing? The square root is taking the right half plane. Now, we haven't answered the full question yet. It's taking the right half plane. All the r values can go as large as they want because the square root's a monotone function. It might take a little bit longer, right? In other words, if I plugged in a point of modulus 4 over here, that would get sent to a point of modulus 2 over here. So there's also not only an argument contraction, there's a contraction of the modulus as well, right? It's not indicated in this picture because what's happening is everything's being smushed, right? So I'm trying to say that if there was a point over here of modulus 4, right, where would that go into this mapping over here? Well, if this was pi over 4, then this would go to what? It would go to pi over 8, and it would go to what point? It would go to the point of modulus 2, right? So in other words, that length of 4 contracts to a length of 2, right? So there's a contraction in the modulus as well as a contraction in the arguments. And now we can see what's going to happen. So if I extend this now to the whole picture, what's going to happen? So now, if we look at the whole slip plane, here's x, here's y, and then here's my branch cut. I need to get Brian Branch on here, right, to do like a promo for these videos, right? That's probably, I probably couldn't afford to get Brian Branch on here, but one of my favorite players. Okay, what's going to happen now? Well, now these arguments over here are between 0 and pi, right? Good. Those arguments get cut in half between, if I cut 0 in half, 0. If I cut pi in half, pi over 2. These arguments over here are between 0 and negative pi, right? If I cut those arguments in half, what happens? It's going to go between 0 and negative pi over 2. So now you should be able to see the following. You should be able to see that this mapping over here, u and then v, is going to take the entire complex plane that's slit and map it where? Map it to the whole right half plane over here, right? And your branch cut gets split up too, right? So these are the negative values. Where's the branch cut going? The branch cut is going over here and over here, right? So now the imaginary axis is now forbidden over here. Excellent. Now, of course, the cool thing you can also do is you can also say, I can find nicer formulas for these things over here. I can say that u is equal to what? I can say u is equal to square root of r and then square root of 1 plus cosine theta over 2, and v is equal to the square root of r square root of 1 minus cosine of theta over 2, right? And so your level sets, so C1 equals u is the same thing as C1 equals u squared, right? If I square it, so the level sets implies C1 squared is going to be r and then 1 plus times 2, of course, times 2 cosine theta, and then C2 equals v implies that C2 squared is equal to r 1 minus cosine theta. And you can remember these graphs from pre-calculus. Those graphs look like sort of like parabolic shapes, right? And of course, they have to intersect at right angles, right? So you have two overlapping sets of shapes that basically look like this. One collection looks like this, and the other collection looks like that, right? So those are your level sets of the real and imaginary part, and they're contracting, of course, the argument by half, contracting the modulus by half, right? This gives us sort of another sneak peek into the theory of Riemann surfaces, which is very important, right? Because I know that there's two solutions to this. You know, if I say z squared is equal to c, there's two solutions to that, right? So in some sense, I have to build up a theory which allows me to have two solutions, multi-valued functions, and the square is sort of showing you where you need to cut the complex plane to change the geometry. I can cut the complex plane along that branch cut, and then sort of lift the complex plane up with respect to the argument structure, right, in such a way that I can actually get a multi-valued function which exactly corresponds to the inverse of this thing, right? And that's what the idea of a Riemann surface at a very, very simplistic level, right? So we'll talk about Riemann surfaces later in the course. But for now, we really want to build intuition for how these conformal maps are working, because the better we are at conformal maps, that will help us solve a lot of problems. A lot of problems in PD, a lot of problems in OD. They transform very nicely under conformal mapping. So we really want to get a handle on how some of the most elementary transformations work, so we're armed with an arsenal of these things to solve differential equations. Thank you very much.